thank you very much for the introduction, and thank you very much for the invitation to Monica and Angela and Miles. So the talk about normalized solutions of nonlinear Schrödinger equations and systems is here. I will report on joint work with two groups. One is a group from two colleagues from China, Wenming Zhou and his student Zhong, and another is a recent collaboration with three people from Italy, namely Riccardo Molle, Matteo Rizzi, and Gian Maria Verzini. So what is this normalized solutions problem? So when you look at the nonlinear Schrödinger equation here, so IDT psi equals minus Laplacian psi plus a potential V psi minus some nonlinearity, F times psi, and you make the standing wave ansatz, so psi of xt is equal to e to the I lambda t u of x, then as you know, you are led to this elliptic PDE. And then about solutions about this, well, let's say there's a huge amount of papers since decades about solutions of this problem, but mostly in the case that this frequency parameter lambda is prescribed. You all know this. There are variational methods, there are topological methods, bifurcation methods, sub-super solution methods, all kinds of approaches to find solutions of this. But for the solution of this time-dependent Schrödinger equation, the L2 norm of the solution is constant. It's independent of t, of the time. So it makes sense to prescribe the L2 norm of the solution. So that means when you look at this problem here, this semi-linear elliptic PDE, we now try to find solutions where we prescribe the L2 norm of u. The term lambda will then be an unknown of the problem. And so this is basically what the normalized solution problem is about. I will talk about systems, an equation like this, and also about a system. This has received lots of attention in recent years, but still it's relatively unknown compared with the problem when lambda is prescribed. Okay, to get some feeling, let us look at this very special nonlinearity, simply the pure power nonlinearity. We look for positive solutions, U in H1, and then it is well known that this has a solution which is radial and unique up to translations. And now one can ask, well, which L2 norms can be realized by these solutions? Well, when you do this, a simple computation shows you that the solution for the parameter lambda is obtained by the solution for lambda equals 1 by simply this simple rescaling. Then you can, of course, compute the L2 norm of your lambda, and you see that you have some L2 norm for the problem with lambda equals 1. You see you can achieve all L2 norms except if the exponent n minus 4 over p minus 2 is equal to 0. Then the L2 norm does not change. It's always the same for lambda in this particular case. So then this is a kind of critical exponent in this setting. So this is the exponent p equals 2 plus 4 over n. And let me just collect this. So for this problem, if p is, what we just observed is, if p is different from 2 plus 4 over n, then this has a solution for all prescribed L2 norms. The parameter lambda, of course, and the solution depend then on the L2 norm, on the prescribed L2 norm, and the solution is then also unique up to translation. So if you just work in the radial setting, you would have a unique solution, but you can realize every L2 norm. However, if p is equal to 2 plus 4 over n, then you only have a solution if a has precisely this value of the L2 norm of the solution for lambda equals 1. And then you have, in this case, you have an unbounded one parameter family of solutions, namely the scaled family U sub lambda, and of course, plus their translates. So this exponent 2 plus 4 over n is, let's say, called the mass critical exponent to this, and it's the second critical exponent in addition to the Sobolev critical exponent, which appears here. Okay, this exponent also plays a role for the time-dependent nonlinear Schrödinger equation, and that just be very short in that if you are mass subcritical, so if P is less than 2 + 4 over n, then this solution has a global existence for all initial conditions in H1, and the solutions are bounded. In the case of a critical exponent, so the mass critical exponent, there is global existence, but the L2 norm of the initial condition has to be small. And for other initial conditions, you have blow up. And if P is bigger than the mass critical exponent, then you have global existence if the H1 norm of the initial condition is small. And again, you have blow up in general. Okay, so now how does one approach this normalized solution problems? First of all, I will present two approaches. One is the variational approach, and later I will also present a topological approach. But most papers here in this topic use the variational approach. So you simply take the energy, which is here the integral over gradient u squared plus v u squared minus the primitive of little g, capital G of xu, and you constrain it to the L2 sphere. So there is no lambda appearing here in the energy. The lambda appears here as a Lagrange multiplier when you look for critical points of J constrained to this sphere S sub A. Okay, so that looks very much like a standard variational problem. Let's also try to understand a bit the role of this mass critical exponent in this setting. So now let's go back to this explicit pure power nonlinearity. So we look at this functional here on the sphere of L2 norm is equal to A. Then an important role plays the Gallardo-Nirenberg inequality. So then you can estimate the LP norm of U by the L2 norm of the gradient and the L2 norm of U to a certain explicit power. Gamma is given explicitly here by this number. Now the L2 norm of U is in our setting just fixed, this fixed number A. So if you plug this inequality into this energy functional, you see that the energy function is bounded below by the gradient U squared minus a constant times the integral of the gradient U squared to this power, gamma P over 2. And then if you are, for instance, interested in the case whether the energy is bounded below on the sphere, then this is, of course, the case if this exponent is less than 1. So if gamma P over 2 is less than 1, then J is bounded below and coercive on this sphere, and you may try to minimize J. And this condition, gamma P over 2 less than 1, is in fact equivalent to P is less than 2 + 4 over n. There's also another setting when J is bounded below and coercive on the sphere, namely if P is equal to 2 + 4 over n, so you have a 1 here, but A is small, so that this coefficient is small, less than 1/2. Then you also have that J is bounded below and coercive. So in this case, this mass subcritical case, of course, you can try to minimize the functional. So let's look at this case that also in a general setting, now if G is mass subcritical, or if it is mass critical and the L2 norm is small, then as I just said, this function is bounded below and coercive on the sphere, and you can try to find solutions of our problem by minimizing the functional on the sphere. As a model nonlinearity, you can simply take here the sum of powers, but here each of the exponents should be mass subcritical. And this minimization, there's work already in the 1980s by Lyons and Stewart, also for more complicated problems. But the problem is even up to now, it is offers interesting challenges. So that means precisely for this problem, Ikoma and Miyamoto wrote a nice paper where they found conditions on G for relative general class of G, but being mass critical. And they found conditions of V so that V of X converges towards 0 quite fast, like 1 over norm X, I guess, at least, so that this infimum is achieved. Okay, for this talk, I will be concerned with the Mars supercritical case. Okay, then the functional constraint to the L2 sphere is not bounded from below. It's unbounded from below and from above, and there does not exist a local minimizer in general. So let us first look at the autonomous case where there is no potential and where G does not depend on X. Then there was a first result, which is already now more than 20 years old, under these two conditions. Namely, you take just a continuous odd function G, and it grows like this. You can control the growth, of little g in this way, and this considers, or let's say contains, the case of this model nonlinearity. Now all exponents are Mars supercritical, but Sobolev subcritical. So under these conditions, then there was a first existence result of normalized solutions, namely by Louis Jean-Jean from 1997. And he proved that this problem has a radial solution for every L2 norm A. You can prescribe the L2 norm, you find a solution, lambda actually being positive, U will be a radial solution, as I said, for every A. And let's say a few years ago, in a joint paper with Sébastien de Valeriona, we improved that under the same setting, under the same conditions, we even have unbounded sequence of radial solutions, again, for every prescribed L2 norm. And actually, in these last 5, 6, 7 years, the problem has found considerable interest. And so these results have been extended to quite a number of general equations. Here I listed a few, like quasi-linear Schrödinger equation, Schrödinger-Poisson equations, Choquard equation, fractional equations, systems, whatever. So let me give you a short sketch proof of this result of Jean-Jean, because some of the methods will appear also later, and one can see already the difference to the problem when one does not prescribe the L2 norm, but prescribes lambda, and the L2 norm is free. So how does the variational approach work? So you take, in this setting, you can work on the space of radial functions. So we take our functional, look at the L2 sphere is equal to A in the space of radial H1 functions, and look at this scaling. This scaling plays an important role. It preserves the L2 norm. So in particular, if you start with an element U of the L2 sphere and you scale it, you have here a nice path on the L2 sphere. And you can easily check what the functional does if S converges towards 0 or converges towards infinity. Namely, if S converges towards 0, then J of S star U is positive and also converges towards 0. And if S converges towards infinity, then J of S star U converges towards minus infinity. So if G is a pure power, then actually this function J of S star U as a function of S has a unique maximum point. And this is so you see a typical mountain path setting. For S near 0, of course, S towards 0 is you just can talk about weak limits. So you don't have 0 here as an element of your sphere. But for S near 0, or for the L2 norm of the gradient of U to be small, being small, then J is very close to 0. And it becomes larger if the L2 norm of U becomes larger, but in the end, it converges towards negative infinity. So here we are in a typical mountain path setting. So to be more precise, that the mountain path structure is as follows. You find there exists a number rho, positive number rho. So, and then you look at those U in the L2 sphere where the gradient of U in the L2 norm is equal to rho. So this, the gradient of the L2 norm, or the L2 norm of the gradient to be equal to rho separates the sphere, the L2 sphere as a red, into two disjoint components. And then what the mountain path structure says, there exists an element U1 in one component, the one where the L2 norm of the gradient is small, less than rho, and U2 in the other component, but J of U1 and J of U2 are less than the infimum. So this would be kind of the mountain range of the L2 sphere. So now, of course, once you have this mountain path structure, you immediately get a Polysmall sequence. And then one starts with the usual procedure. You prove that it is bounded, pass to a weak limit, and then see you hope to get to arrive at a solution. But first of all, to get a bounded Polysmall sequence, in the case that when you do not prescribe the L2 norm, but you have your work in the full space H1, no constraint, then for the bound you look at this variation of J. So you look at J prime of UN, you vary it in the direction of UN. But this is not allowed here because since we only have a Polysmall sequence for the constraint functional, we have this identity here. So the J prime of UN is equal to O of 1. Here we can only plug in elements in the tangent space of the sphere. So we can put in here elements V such that they are L2 orthogonal to U sub n. So we cannot use this. Now there was a nice idea of Jean-Jean, namely he looked at the functional J of S star V and had S as an additional parameter. So V is in the L2 norm, it has L2 norm equals A, so it's in the L2 sphere. S star V lies in the same sphere. So we look at this path, take it as a function of S and V, looks like this here, and see that a mountain path structure for J gives actually a mountain path structure for J tilde. And then you get a Polysmall sequence, but now consisting of a positive number S sub n and an element V sub n of the sphere for the constraint functional. Now, Polysmall sequence means that the gradient of J tilde of U at Vn is, let me put it differently. If you look at Sn star Vn, then you get actually a Polysmall sequence for J. And this is obtained by taking the derivative of J tilde in the direction of U at the point V sub n. But then you can also take the derivative in the S direction, and you get a scalar equation, an additional condition, namely this P of Un, this integral of gradient Un squared plus capital N of this integral G of Un minus N over 2 integral G of Un dot 0, that this is the, let's say, an additional condition which is actually needed or can be used to prove that this sequence Un is then a bounded Polysmall sequence. Observe that the identity P of U equal to 0 is the Poiseuille identity, which is satisfied by solutions of our problem anyway. So with this trick of Jean-Jean, we get a Polysmall sequence for our functional J, such that also the Poiseuille identity is almost satisfied. Okay, so being a Polysmall sequence for J means, first of all, there exists some Lagrange multipliers, so that this equation minus Laplacian U plus lambda U equals G of U is almost satisfied by UN. UN is bounded. You get a weak path to a weak limit. Of course, then the weak limit need not lie on the L2 sphere, so you just know that the L2 sphere is less or equal to A. In any case, to proceed, what one needs now is to control the Lagrange multipliers. And in this setting, one can prove in the next step that the Lagrange multipliers actually do converge towards some positive lambda. And then once one has shown this, that U sub n also converges strongly. And this argument, of course, uses the compact embedding of H1 of the radial functions in H1 functions into LP for P between 2 and 2 star. And so you have a critical point of the constraint functional and a solution of your problem with the prescribed L2 norm being equal to A. For the infinitely many solutions, one uses the symmetry that the functional actually is an even functional. J of minus u is equal to j of u. And this is a symmetry argument which we established in the paper with Sébastien de Valériola. And actually, for this there was a topological argument needed, and there's a simpler proof in the recent paper with Yan Liu and Charlie Liu, where we consider the nonlinear Shokar equation. Okay, but oh yeah, maybe just a short variation of the proof that you can take this Poisson identity also as an additional constraint. So that means you look in the A2 sphere and you include the Poisson identity as an additional constraint, P of u is equal to 0. So you have a codimension 1 submanifold of the A2 sphere, but submanifold has to be taken with a grain of salt. It is not a manifold in general, but still one can do some critical point theory on this P sub A. One can prove that the infimum is achieved, and that now this infimum here is actually corresponds to the mountain pass value for the functional on the sphere. This is now an infimum on the Poisson manifold. And also there's a more classical genus type argument for the constraint functional of J to P sub A. This is also achieved. And this method has been established in some joint work with Nicola Soave for systems actually, and Nicola extended it to this problem here for quite general, more general classes of G. Okay, now you see, I would like to leave this autonomous region and would like to see what happens if some potential enters. And this changes the situation quite a bit. So it's clear that the scaling well, it can be used, but it's not as easy to use and requires some additional work for sure. So let's look at this model problem here. So we just add the potential V of xu, and I consider the case that V of x vanishes at infinity. So V is in L infinity of Rn. I just take the pure power here with P being mass supercritical and super less subcritical, and assume that V is positive and converges towards 0 as norm of x towards infinity. And I also need that the function V of x times norm of x also lies in L infinity. So you see V of x converges towards 0, like is 1 over norm x almost. Then we can prove the existence of a solution if, in addition, the L infinity norms of V and W are not too large. This result is not of a perturbation type. So that means we do not say there exists C1 and C2 such that if these norms are the L infinity norms of V and W are small, that then we have a solution. So we have explicit definitions for these bounds. For sure, they are not optimal, but they just tell us that the result is not just a perturbation result. And we have a similar result also if V has singularities, and this would require that V is then in a Lebesgue space of class n over 2 on Rn. So this is nice, but the difficulties which the potential presents can be seen from the following remarks. Namely, first of all, actually we do not know of any potential V such that this has a solution for all A. Would be interesting, but maybe it cannot be expected. But so anyway, we don't have any examples of any V, even in the pure power case. Also, without the V, we have an unbounded sequence of solutions for every A. Here we don't even know about the existence of a second solution, possibly sign changing for the problem if V is different from 0. And also the argument does not work for a general G of U. So this means that it does not mean that this is impossible, but one definitely needs more refined arguments if one wants to deal this, to address these questions or remarks, or let's say these open problems here. So how is the situation here? Again, I am in the setting of the variational approach. So first of all, we observe that the functional has now this additional term here, but it has actually the same mountain path structure as the functional J infinity. So J infinity of u is well understood in our setting. So we have a nice mountain path structure. Namely, there exists, to remember this, there were two numbers, there were two elements u1 and u2 in the L2 sphere, separated by the L2 norm of their gradients in this way, such that the value of J infinity, this was the J from the original problem, now with the explicit pure power here, so that J infinity of u1 and J infinity of u2 is less than J infinity if you look only at those u in this L2 sphere where the gradient of u in the L2 sphere is equal to rho. Now, I say this has the same mountain path structure, and then you can take u1 and you shift it by some element y in Rn. If you make the norm of y large, then this energy here, the energy of u1 of evaluated at x minus y, of course converges towards J infinity of u1, because v converges towards 0 as norm of x converges towards infinity. So this J of u1 at minus y converges towards J infinity of u1 and this here. And the infimum of J on the L2 sphere, when the gradient of u has the L2 norm rho, is even larger than this J infinity of u here, because v is greater or equal to 0. So J of u is greater or equal to J infinity of u. So the mountain path structure is the same, with the same mountain path value, but actually it is not achieved, because you see already here what happens. You have a vanishing for the mountain path value and also for Polysmall sequences. So first of all, that means we need a different kind of linking. Let me now describe the linking. So we start with the unique positive radial solution of this problem here with the prescribed L2 norm of u. So then there's also a particular value of lambda. There's a unique solution. And then we look at H1 star u and H2, sorry, the Z is here wrong, this is too much. So H2 star u for H1 small and H2 large. If H1 is small, then this converges towards 0. And if H2 is large, this converges towards infinity. Okay. And then we look for, let's say on this kind of cylinder, we take the ball of radius kept some radius r in Rn times the interval H1, H2. Think of r being large, H1 being very close to 0, H2 being also large. And then we look at maps from this Q into the sphere, continuous maps, which on the boundary of this cylinder, so where either y has norm r or h coincides with h1 or h2, for these values we take gamma of yh just to be our u shifted or translated by y and scaled by h. So we take our solution u. If you fix y, let's say, and take h as parameter, then we almost approach a mountain path for the functional. But we make this mountain path for all y with norm y in Rn with norm y large. And we propose that as a minimax value, we take the infimum over all such continuous maps over the maximum of all yh in the cylinder, and we evaluate j J, the function at gamma of YH. So you see, this is kind of an n+1 dimensional linking. When of course, the result will be that this actually is a critical value. The corresponding critical point U will then be have Morse index n+1 as a critical point of J constrained to the L2 sphere. Okay, so first of all, now here's the linking. We actually do have a linking. What we can prove is there exists a large number R. H1 is small, H2 is large. Such when you make this inf max, this was our inf max value, or our critical value, then this is actually larger than the supremum over all gamma when you take the YH just in the boundary of Q. Because of this inequality, you can start the standard argument, and it tells you there exists a Polysmall sequence on this level n sub V of A. In addition, with our assumptions, we have that this value is bigger than the mountain path value, but it is less than twice the mountain path value. So this is, of course, where our assumptions on V and enter, on the L infinity norm of V. So then we continue, of course. Now the argument will be the same. We prove the existence of a bounded Polysmall sequence with corresponding Lagrange multipliers, and then having achieved this, we prove that Lagrange multiplier actually converge along a subsequence, and the U sub n also converge strongly. And for the step 2, we make a similar argument as before. We also evaluate J at S star V and take S as an additional free parameter. Now the function, you see the term with the potential enters, and you see here why one has a little bit, let's say one cannot scale out the parameter S from the argument here, X here. But then the final arguments here are, I mean, we can use this to get the bounded Polysmall sequence, but then to conclude, since now we cannot work on the space of radial functions, we don't have a compact embedding, and then we need a more refined argument, a splitting lemma for the Polysmall sequences of this constraint problem. And actually, this is already needed at this setting for step 1. And we also use that this problem here has a unique solution in H1 rod, in a positive radial function. Okay, so this argument is more complicated, but the idea is, let's say the sketch of the proof is similar to the case without the potential. But as I said, so the argument is subtle. Without the L infinity norms of V, we do not quite know about, we need this estimate, for instance, that the critical value is less than twice the mountain path value. So this will be, is getting certainly more subtle without L infinity norms on the potential V. Okay, so this was the last, what I wanted to say about the equation. And also the last, what I want to say about the variational approach. I now want to present a topological approach, which can also be used for the equation, but I prefer to present a different topic, which has been quite popular also in the last years, namely to look to consider such a system, which has been really since investigated. You see here some papers from about 2005, since about 15 years. But now we want to assume also L2 normalization constraints for the two components U and V. So it is just a nonlinear Schrödinger equation for U and V coupled in this way. And this is a typical coupling which appears in models for binary mixtures of Bose-Einstein condensates. So without the L2 constraint, but with the lambda I being fixed, then you see here a number of papers from starting 2005. And I stopped with papers appearing after 2007, because then there is an explosion of such papers. And so I can imagine that a number of people in the audience have worked on the system. So please don't be angry about me. I just stopped here at 2007. So now we are interested in the L2 normalized solutions. And then this system has been considered only more recently. I present now a quite recent type of result. It appeared last year online in Mathematische Annalen. So we take the system and obtain solutions if this parameter beta lies in a certain range. The range where beta lies is given by the values mu1 and mu2, which we assume to be positive, and a number tau 0, which is also explicitly given. You take the solution U of this problem here, the unique positive solution here of this problem, radial in H1. You take this inf. This is a number between 0 and 1. It's not difficult to prove. And then we want to solve our problem with lambda 1 and lambda 2 now being part of the problem, but L2 norm of U and L2 norm of V being prescribed. And the result says if beta lies either in this interval or in this interval, then this has a solution for any AB positive. So I tend to conjecture that this result is optimal, meaning that this range is optimal. At least we can show that for some beta which are not in this interval, that the solution depends on the ratio A over B. So there's no solution for, there does not exist a solution for all pairs of values A and B. And this result improves earlier result with Louis Jean-Jean and Nicolas Soave, where in this earlier result, actually, we had the value of beta such that a solution exists also dependent on A and B. So in this earlier result, there was not one value of beta so that we would have existence of solutions for all values A, B. The paper with Jean-Jean and Soave there we used the variational methods, and just to be short, there's a functional associated with it. We constrain it to the L2 spheres, for both components. It's now a product of L2 spheres in H1 times H1, just the radial setting. This has been not just considered in some work with Jean-Jean and Soave, but also Go and Jean-Jean and Nicolas continue to work on that, also for more general cases, more general exponents here instead of exponents 4 here and 2 here. They were more general exponents, and both where the exponents are mass supercritical and mass subcritical. So this has been considered in other papers. So I don't want to go into details because then the results get technical. Anyway, and also there's a nice paper by Norris Tavares at Versidi. When they have potentials, but they have trapping potentials, that means there's a V of x converging towards infinity as x towards infinity. Okay, so what I would like to approach here is to present now in the last minutes is a topological approach to this problem. So we take the problem, we do not prescribe the L2 norms, we take lambda 1, lambda 2 now as a free parameter, and investigate simply the range of the L2 norms for the solutions that we can find. So that means just solve it and see what can we say about the L2 norms of the solutions U and B. And now the idea is to use bifurcation and continuation methods to find global connected continua of solutions so that the L2 norms vary continuously. And if you happen to know that the L2 norms of U vary continuously between 0 and infinity, then with varying lambda 1 and lambda 2, then you get solutions for all values of A or B. So that is a kind of simple-minded approach. And we can first, now in this setting, we can first, with this explicit nonlinearity is homogeneous, we can first reduce to one parameter. So the second parameter is just can be normalized to 1. So this is just a rescaling. And the result is, if you have a solution of this problem with some parameter lambda greater than 0, then you have so if you have a solution of this problem 7, then you get a solution for our original problem for L2 norms of u equal to a, L2 norm of v equal to b, if this ratio is the same. This is a simple rescaling. So we just can concentrate on this problem here, just one parameter less. And now the idea, of course, is we take the set of all solutions of this problem 7, consisting now of triples, lambda, u, and v, which solve it, and look at the ratio of, or the quotient of these L2 norms of u divided by the L2 norm of v, and see which ratios appear. And if this function rho sub beta is onto, then all ratios appear, and then you have a solution for all values of a, b. That means for arbitrary prescribed L2 norms of u and v. So that's the first idea. And as I said, now we try to apply bifurcation results. So we allow now for the moment that u or v are also equal to 0. Because then we have trivial, or what I sometimes is called semi-trivial solutions. This is the case if one of the components is equal to 0. So for instance, if v is equal to 0, then this part here drops, and you just have this equation and you know everything about it. So you have a positive solution. So that means, which we call u lambda mu1. So if the v is equal to 0, then you have a solution for the first equation, the positive solution and the positive radial solution. Similarly, if u is equal to 0, you also have a solution of the second equation. Now there's a 1 here because this corresponds to the factor 1 in front of the v here. So we have two nice branches and explicitly known branches of semi-trivial solutions. And of course, we also have the trivial solution branch where both u and v are equal to 0, which exists for all lambda. And now let's see, can we prove bifurcation from this set of solutions? And for reasons of time, I cannot go into the details, but here is the semi-trivial branch. This is the case where u is equal to 0, then v does not depend on lambda. But if this is the branch where v is equal to 0, here the solution u depends on lambda, because there was the minus Laplacian u plus lambda u. We investigate when bifurcation takes place from the branches T1 or T2. It's easy to see that there's no bifurcation from the branch of trivial solution. This is also this branch here. There's no bifurcation from this branch. This picture on the right just tells you something, that depending on beta, we have bifurcation either from both branches, T1 and T2, or only from one branch, or we have bifurcation from no branch. This depends on beta, and I will consider now just one case, that beta is bigger than tau 0 max. This is the case when you have bifurcation from both branches. So how do we proceed in this setting now? First of all, we compute the bifurcation points along the branches. There's precisely one on each branch. Then we formulate the problem as a fixed point equation. So we have an operator, nonlinear operator, which depends on lambda and on beta. Beta is now fixed here. Lambda is our bifurcation parameter. A lambda beta of uv is equal to v. This is the fixed point equation formulation of our original problem. We just look for problems in the cone of positive functions, u and v both greater or equal to 0. Then we compute the local fixed point index. There is a fixed point index, so this is with respect to this positive cone of this operator. So this is a descendant of the Leray-Schauder index. And if this fixed point index changes, then there's bifurcation of solutions. And since this is and the bifurcation goes into the positive cone. And since it's an in the end, it's a kind of degree type argument when it actually has a global branches. So as I just said, if the index changes along a branch, then you have connected subsets S1, S2 bifurcating from T1 and T2. These are subsets of lambda of R plus times P, lambda in R plus, U and V in this positive cone P. And I just drew here the bifurcating branches near the bifurcation points. And now one has to investigate what happens with these branches. And now there are now several possibilities. It could be that the branches connect, but this means that then this rho sub beta is equal to R plus. This is obvious. You see, what is rho sub beta of an element lambda uv on this branch? You simply take the L2 norm of u divided by the L2 norm of v. But if here in the neighborhood of this point, we have u is equal to 0 on this T sub 2. So along this branch, this quotient converges towards 0 because the L2 norm of u converges towards 0 and the L2 norm of v converges towards a fixed positive value. So this rho sub beta converges towards 0. It's just the other way around at this bifurcation point. Here the LP norm of v is equal to 0. The L2 norm of v is equal to 0 on T sub 1. So if you approach T sub 1 along this red connected set of solutions, then the quotient L2 norm of u divided by L2 norm of v converges towards infinity. So in this setting, since this is a connected branch connecting the two branches, T1 and T2, you have that rho beta is onto, and you have a solution of our original problem for all values a, b. Of course, it can happen that the branches do not connect, but then the branches must connect either, or let's say, to lambda equals to 0 and lambda equals infinity. They are, after all, they are unbounded branches, and one can prove that as long as lambda is bounded away from 0 and from infinity, then the u and v are also bounded. So if the branch to be unbounded, the lambda term has to converge towards 0, or it has to converge towards infinity. And then one can again make an analysis of the L2 norms, and one observes again that rho sub beta is onto. And you again have a solution for all values of a, b. This is the case when you have bifurcation from both branches. It can happen that you have only bifurcation from one branch, or that you have bifurcation, no bifurcation at all. So we treat these cases one by one, and then we get this in the end is the proof of our result. And there's just a particular range of beta values when there is bifurcation, but we do not have these global estimates. And we cannot control let's see, the set rho beta, excuse me, the image of rho beta is not all of R plus, but it's only a part of it. Okay, that is the topological approach. It, in principle, can also be applied to equations and should also give good results. And I see time is over. I don't have much more, let's say, just let me say that there are results also on bounded domains for the normalized solution problems. Again, using this, if you want, a bifurcation type approach. There is bifurcation that's easy to prove and well known. The solution is in particularly well understood if omega is a ball, and I would just like to refer to, here's the bifurcation scenario. I'd like to mention there's a nice result by Benedetta Norris, Pierotti, it's a group of 4, Pierotti, Tavares, and Versini in 2 papers who considered this problem on a bounded domain, in particular for the ball. And again, distinguishing between the case of mass subcritical, you see this scheme here. One has a solution for all A, you can minimize. For the mass critical case, then you have solutions only a certain range for small values of the L2 norms. Or for the mass supercritical problem, again, you have the solutions only for the L2 norm being small. And this is if and only if in case of the ball. So I think that's all I would like to say. And I thank you for your attention.